All right, everybody, and now we are on lecture 2, so section E.3, the reliability of a measurement. So now that we know how to do our units of measurement, it's important to know that not every measurement is going to be reliable. So you guys are going to, and this might be something you do in the lab, and this can even be something you do at home if you have the right equipment. Every single ruler, graduated cylinder, everything we use in lab has a level of uncertainty. This basically means it's not going to be exact. It's not going to be extremely precise. If you want something to be extremely precise when you're measuring it, you want exactly 0.0025 microliters of something, then you're going to have to use an expensive, most likely electronic equipment in order to do that. But when we have graduated cylinders and everything, these are mass produced and they're not going to be super exact. Not every single one is going to be exactly the same. The only type of measurement that is free of uncertainty is counting. Counting provides exact numbers. So if we're looking at here, we see that water kind of climbs up the sides and it has this kind of meniscus. So meniscus is the curve right here. This is called the meniscus, this curve. And this is going to be very important to know because your professor is going to be like, make sure to read it at the center of the meniscus and not at the sides, right? Because the sides tell us that, let's see, if this is between 20 and 25, and this is 21, and this is 22, the sides tell us that this is at 22, right? Because if we look at it from the exact side here, but the meniscus is telling us that it's like 21.5, right? It's like kind of in the middle. So that's what we're going to be reading here. So he went a little bit more exact because it zoomed in a little bit more. So 21.6 milliliters. So keep in mind that this last little red digit here is uncertain, which means we guessed it, right? We don't know exactly if this is 0.6, but it's not 21 and it's not 22. It's a little bit over halfway, so that's why we put the 0.6 there. And make sure you do not forget your units. Oh my goodness, some professors are going to be so harsh, even in the higher level classes. Now we get into this horrible thing called significant figures. So if we're looking here, we have where it looks like we're measuring a lid, and it says 160.90 grams. So how many significant figures is this balance displaying? So then we look at here and it's like significant figures, or sig-figs, which I'm going to refer to them as because it's easier, and again, scientists are lazy. Out of these 5 numbers, which of them are the most important? And we're looking here and it looks like every single one is important, but keep in mind that the final one is not going to be precise. It's uncertain. Usually on a lot of these scales, the very last one or even the last 2 or even the last 3 are sometimes going to be uncertain, which means the scale is kind of guessing based on its parameters. So the final 0 is not certain, it's the best guess. Thus, this value represents any value between 0.895 and 0.904. So if we go here, the 0 is significant here at the end because it's uncertain, and if it's uncertain, it's significant. But here we have a 0.0395 grams. So how many out of these 5 digits are significant? And it's only 3. If there is zeros before your actual number starts, so any number besides 0 basically starts, the leading zeros are not significant. So there's actually only 3 significant figures here. And you can eliminate it by using exponential notation. Noodles and ramen, negative going towards the right, so 1, 2, E, negative 2 grams. So these are the rules for sig-figs. These are very important. So non-zero digits are always significant. 233.1 meters has 4 significant figures. So 2, 3, 3, and 1 are all significant. 2 and 0.3 grams has 2 significant figures. Zeros at the beginning of the number are never significant. This only has 4 and this only has 2. Zeros between non-zero digits are always significant. So if there is a whole number at the beginning and 10 zeros and a whole number at the end, every single one of those zeros is significant. So even if you have a whole bunch of zeros, like if you have 10 zeros between this 2 and 4 and 5, then you might have a massive sandwich, but it is a sandwich indeed. So you have 2.045, which is 4 significant figures. and this has 5 sig-figs. It's very, very important. Zeros at the end of the number that contain a decimal point are also always significant, because remember, zeros at the end are uncertain, because this doesn't mean it could be 0, it could mean something else, right? So 3.00 has 3 significant figures. If there was 10 zeros after this, then it would have 3 and then the 10 zeros, so 11 significant figures. So this, right, the zeros before don't matter, but 2330, 0 being uncertain, the last digit's uncertain, has 4 significant figures. So this is hard. I gave the sandwich example for the first 3 rules, but then you got to keep in mind, after the decimal, it's no man's land. So it can be, as long as you remember the sandwich thing for these, that'll get you through it. And then if you remember at the end, the zeros past the decimal point are always going to be significant. Zeros at the end of a number that contain no decimal point may or may not be significant. So basically it's saying 530. So 530. The 0 at the end, because there's no decimal points here, so 530 with no decimal point. That 0 may or may not be significant. Some scales that weigh things may do it in just the hundreds of grams and have no decimal point, so that's why it may or may not be significant, because it's kind of like the 0 past the decimal point. It may or may not be significant because there's no decimal point. So rule 5 is kind of a very wonky one, and honestly it's best just to say that if there's no decimal point, all but maybe the last 0 are going to be significant. There it is. Yeah, you could say it's a range between 1 to 5 significant figures. So it looks like the professor could want you to put a range there, but again, I'd ask. So if we have here where we can read it, and it seems like it is at 24.2 degrees Celsius. So our 2 is uncertain, but all 3 are significant, right? So at the meniscus, remember, we're not looking at, remember we're reading down on this one. We are not looking at the sides here, because it would give us 1, 2, 3. It'd give us a 1.3. No, so we're looking at the bottom of the meniscus right here, which leads us to 1.4. And you guys can practice with these other ones as well. Just practice, practice, practice. It really, really does help. Significant figures in calculations. So we learned about sig-figs, so that way we could use them in practice, in conversions. So if you travel 157.7 kilometers and then you travel 20.153 kilometers, how many kilometers did you travel? We look here and we see that this only has 1 digit past the decimal point, whereas 20.153 has 3 digits past the decimal point. So the final answer should round to only the first. Basically, the shortest number past the decimal point is the one that you're going to round to. So even though after adding, we end up with 0.853, because 157.7 only has 1 number past the decimal point, we're going to end up with 177.8. Or rounded, because you round if it's a 5 or higher, we'll end up with 177.9 as our final answer. So when you add or subtract, you do worry about where the decimal point is in the starting numbers. However, when you're multiplying or dividing, you have to kind of keep this in mind a little bit more. So if you travel 157.9 kilometers in 189 minutes, and what is your rate of travel between kilometers and minutes? This is very easy. It's kilometers divided by minutes. And then you get this kind of lengthy answer. But you can't give this as an answer because your professor will mark you wrong. So then you got to look. So this one has 4 significant figures total, and this has 3 significant figures total. So the number of sig-figs is limited to 3, which makes our answer 0.835, because remember, zeros before the decimal point are not necessary, so 835 are the most necessary. And this 4 right here is underlined because if it's 4 or lower, then you don't have to round. So this 5 is not going anywhere, so we have 0.835. So when you multiply, divide, you don't worry about where the decimal point is in the starting numbers. You just got to know the significant figures as a whole. So for addition and subtraction, you worry about after the decimal point. And for multiplication and division, you worry about the number of sig-figs as a whole. I don't have a handy-dandy metaphor or something to give you. It's just something you guys are going to have to memorize and learn along the way. For precision and accurate. So this is accurate and precise, right? Accurate means it's close to the target number which you want, and precise means that it is all together, right? There's not a big deviation. Something not precise would mean like a shot here, a shot here, a shot here. Precise means they're all relatively close to each other, and accurate means it's close to the mark. Precise but not accurate means all of the marks are close to each other, but not where they're supposed to be. And not accurate or precise means they're not even close to where they're supposed to be, and they're not even close to each other. So that's kind of very random. Precision and accuracy is very important, especially when trying to measure out something consistently. You yourself can look at each of these dispensers and figure out, are they all close together? That means they're precise. Are they all close to where they're supposed to be? So it looks like we need 296. So which of these is both close to 296 and all 5 are close to 296. So you can look at that and figure that out for yourself. Next is density. Density is very important. Every single compound molecule has kind of its own density. So the density, it's in grams per milliliter usually. It can also be in kilograms per meters cubed for gases, but that's kind of not really useful, but you're usually going to see it in grams per milliliter. So the density of water is 1. So this is very, very nice. Water is so nice. So the density of water is 1 grams per milliliter. Everything heavier than 1 gram per milliliter is going to sink. So that'll be most things, honestly. That'll be us. Basically everything that has more weight than a gram is kind of a good rule of thumb. Everything that kind of weighs more than a gram is going to sink. So a mechanical pencil won't sink because it doesn't really weigh more than a gram, and also the surface tension is kind of like spread out. Surface tension is its own thing, but we can get that later. That's why a lot of like bugs will float on water. So density is grams per liters. This is grams, this is milliliters. So density equals, so D equals M over V. M means mass here. So this is where it gets confusing. This is why you gotta think in the context. We're not thinking in the context of units of measurement, we're thinking in density. So when you're thinking about density, D is density, M is mass, and V is your volume. It's always usually going to be in grams and milliliters, and everything in a red box, honestly, you guys should be memorizing. So water has a density of mass over volume, grams over milliliters at 20 degrees Celsius specifically. 20 degrees Celsius is room temperature-ish. It's slightly colder than room temperature. Room temperature, I think, is 23 or 24 degrees Celsius. So this is an example. So you have a solid with a mass of 83.57 and a volume of 44.6. So if you take 83.57 and divide it by 44.6 grams over milliliters, if it's greater than 1, it sinks in water, and if it's less than 1, it floats. So I highly recommend you guys do this. So if you have a liquid with a density of here, if you measure out 120 milliliters of this liquid, how much will it weigh? So this is when you're going to take this, right? So you know how in the conversions earlier we put what we were given first over 1? Here we're given 1 milliliter basically. So you'll take 0.83, and I highly recommend you write this out as I'm speaking it so that way you can see it. Take 0.83468, right? This one right here, grams, and then you put a line under it, over 1 milliliter. So this number, this amount of grams over 1 milliliter, and then you're gonna multiply all of that times 120.0 milliliters over 1. So now you can see that we have grams over milliliters times milliliters over 1. So your milliliters cancel out. So that leaves you with this number multiplied by 120, and the milliliters cancel out, leaving you with just grams. So you'll have whatever the number you've calculated it, and that is the amount of grams. So if you measure out 120 milliliters of this liquid with this density, it will weigh this much. So what will be the volume of a solid with a mass of 2.9 times 10 to the negative 2, or E negative 2 grams, and a density of here? So you'll take your grams over 1. So keep in mind that 2.9 E to the negative 2, you can't put that in your calculator. You can put 2.9 times 10 to the negative 2 in the calculator, but it's kind of easier because negative 2 kind of small. You just go 1, 2, 0.029 grams over 1 times, if grams is on the top, then we can't multiply it by this, which has grams on the top also. We'll have to flip this upside down, times 1 milliliter over 1.34 grams. And you'll end up dividing these two, and that is what the milliliters are going to be, or the volume of the solid. So next is energy and units, E.6. We are zooming through section E. So these are very important definitions. I highly recommend you writing this down, either on note cards or flashcards, just to kind of get yourself kind of into it. So energy is the capacity to work. Work is the action of a force over a distance, and the total energy for an object is the sum of its kinetic energy and potential energy. Kinetic energy, the energy associated with an object's motion. So kinetic energy is when something is moving. Potential energy, the energy associated with an object's position or composition. And thermal energy associated with the temperature of an object. So if we take this, for example, it looks like we have a 2-story building and we have a 10 kilogram weight. So the weight doesn't quite matter too much right now. We're not thinking about that, but the weight being really up high has very high potential energy. It has the potential to have a lot of energy, basically. That's an easy way to figure out what potential energy is. It has the potential to do a lot of energy. So if something has 0 potential energy, it's probably sitting here and not doing anything. If it's like on the ground, it will most likely have like 0 potential energy because it can't go any further. But if it's way up high, gravity is pulling it down, and because it's heavy and gravity's pulling it down, it has high potential energy. Once it falls off and it's in motion, then it has kinetic energy. Kinetic energy is only when it's in motion. It won't have kinetic energy here, and it won't have kinetic energy here. All right, so this is going into a little bit of physics. Energy, we've been talking about it here. It's the capacity to do work. So if you say, oh, I'm really tired, I have low energy, we don't have a lot of capacity to do things. We don't have a lot of capacity to do work. Work is the action of a force over a distance. So basically, you can do work on a box by pushing it, applying a force to it, basically pushing it over a distance. And then the sum of the total energy for an object is the sum of its kinetic energy and potential energy, right? And the thermal energy, once it hits the ground, it actually gives off heat. So if you rub your hands together, you're creating thermal energy. The sun is creating thermal energy. If something falls from a height, and like maybe under this, once it struck, the ground was a little hot, that would also provide thermal energy. This is a very important equation you guys should memorize. Ke, or kinetic energy, equals half of mv squared. Remember, in this context, m doesn't mean meters or anything. M means mass, and v means volume. Velocity. Sorry, volume is going to be capitalized, I believe. So lowercase v is going to be velocity, which is meters per second. So 1 meter over 1 second. So the standard international unit of energy is the joule. Joule is energy. 1 joule means 1 kilogram times meters squared over seconds squared. So that is another way to write 1 joule. But instead of writing this horrific thing like times 10 to the something, we could write it like e to the something or 1 joule. That's kind of like a comparison there. So also here's some other conversions with kilowatts and calories. And this is another table to help convert in between everything, and it's telling you kind of the amount required for to kind of like use everything, calories and energy. But this is a very kind of important thing to use here. So changes in energy. Energy is neither created nor destroyed. This is the first law of thermodynamics. You guys are going to need to know this, but it can be transferred from one object or system to another. So energy can never be lost. It can never be created, never be destroyed. However, you can transfer energy to something else. So like when a bowling ball strikes some pins, the pins go flying and the pins got the energy of the bowling ball, and the bowling ball slows down because the energy got transferred. Processes in which an object loses thermal energy to its surroundings are referred to being as exothermic. Like this feels hot. Like an exoskeleton of an ant means it has a skeleton on the outside, whereas humans have like an endoskeleton. We have our skeleton on the inside. So remember, exo is like exit. So exit meaning to give off. So it loses because exo means to leave or give energy to the outside. It means it's losing energy. So you guys are going to have to know that. And if you know exothermic means to lose energy, then the opposite of that is endothermic, which means to gain energy and take from its surroundings. So exothermic would feel hot and endothermic would feel cold. So that's kind of the difference between this right here. And with that, that concludes lecture 2.